So one of the things we'll be interested in with sequences is where they're headed. In the long run, do they converge on some value? Are the numbers in that list getting closer and closer to some value? Now, if you think about it, there's not much we can do with a sequence as far as limits are concerned, right? I mean, with functions, you could talk about the limit as you get closer and closer and closer to 2 or 3 or any number along this axis. But you can't approach any of these values, right? You don't come in closer and closer to that dot. You skip from that dot to that dot to that dot. So there's these huge gaps, right? So it makes no sense to talk about the limit as this sequence approaches 2 or 3. You don't approach it. You're just there all of a sudden, right? You just hop straight from that dot to that. So limits don't really make any sense other than limits as you go out to infinity, right? Where are these dots headed as we go farther and farther and farther out in the sequence? So we'll be looking at really only limits at infinity. And really, in general, besides just limits, it doesn't make sense to talk about derivatives, right? There's no tangent line because there's no continuity, right? We have no continuity here. We skip always to the natural numbers. There's no derivative. There's no integral. There's no continuity. So any of that stuff is out the window. But we are interested in where these numbers are headed. And because often where the numbers in a sequence are headed are tied to whether or not the sum of the sequence, or the series, converges or diverges. So we look at sequences first because they're kind of the building blocks of series. So what do we mean by convergence for a sequence? Well, we mean the same thing we meant for limits at infinity for functions. If you look at this definition of convergence, it's saying we converge to L if for every epsilon greater than 0, there exists a big N such that that is true for all n greater than big N. So what is that absolute value thing saying? It's saying that the terms, the distance between our terms and that L are shrinking and shrinking and shrinking down to 0, right? Because you're allowed to pick any epsilon greater than 0, so you can keep tweaking that epsilon, making it smaller, 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 and smaller, and smaller. But there'll eventually be a point, and that's what that n bigger than big N means, right? It's not going to be true at first that all of our terms are within epsilon of L, but there will reach a point at which that becomes true, right? So what I'd like to do is use that definition to prove a limit. And we'll use something very intuitive, 1 over n, right? We know enough about what's going to happen with those numbers to recognize that those are just going to shrink down and get closer and closer and closer to 0, right? 1/5, 1/6, 1/7, 1/8. I want to formally prove that from the definition of convergence. So let's show that this thing converges, and specifically, it converges to 0. So I want to prove that the limit as n goes to infinity of 1 over n is 0. And if you recall from Calc 1, you proved this for the function 1 over x, and the argument was very similar because the definition was really the same. If you change all those n's to x's and the a to f, you basically have the definition you had in Calc 1 for the limit at infinity of a function. OK, so what do I need to prove? I need to prove that if you give me any epsilon greater than 0, I can find that big N such that when I'm out past that, I'm that close to 0. So, in the notation of that, this is our L, right? So L is 0. And in that notation over there, the a sub n's are 1 over n, right? So what I want to start off with is say you give me any epsilon bigger than 0. So say epsilon is some number bigger than 0. I want to figure out how far out in my list do I have to go before I'm that close, that distance from 0. So you can think of the epsilon as a boundary here. You pick some epsilon. That's going to be some distance from your limit. In this case, we're going to prove that the limit is 0, that it's this axis. So when you pick epsilon, you're picking some distance from there, really on both sides, although this sequence is strictly positive, so the negative side doesn't really matter that much. But what you're saying is, okay, given some epsilon, if I go that much on either side of L, right, because it's the absolute difference. So everything within that range is within epsilon of L, right? And that's what that statement says. AN minus L in absolute value is less than epsilon. So anything within here is within epsilon of 0. Now I just drew some arbitrary location there, but the idea is we want to figure out, okay, in this little picture, for this epsilon I happen to have drawn, it would be right here, right? This point is now within epsilon, and every point after that, if we kept drawing our dots, all dots after that would be in that zone, right? That zone that is an epsilon away from 0 on either side. And that's what the big N is. The big N is that point at which then, I guess, everything past 2, it's true, right, in this picture. In this picture, the big N would be 2, because once you go past 2, every dot is going to be within epsilon of that. So what we need to prove, this is just a specific picture. We want to prove that this can be done no matter how tightly you squeeze that in. So you can make those epsilons smaller and smaller and smaller and make that zone smaller and smaller. But there'll always be a big N that once I get there, all dots after that will be within epsilon. So that's what I want to show. So let's write that expression. We want the absolute value of AN minus L, which is 1 over N minus 0, to be less than epsilon. Well, 1 over N minus 0 is just 1 over N. And in absolute value, that's just 1 over N. Right? So that whole thing just simplifies down to that expression. Now what I want to do is solve that for N. So I know what N needs to be for this to be true. So multiply both sides by N. And remember, with inequalities, you got to be careful. If you multiply by a negative, that inequality flips around. But N is a natural number, 1, 2, 3, 4, so it's not negative, so we're good. No flipping of the direction of the inequality. Now I want to divide by epsilon. So N needs to be bigger than 1 over epsilon. And again, when you divide by, you could possibly switch the direction, but epsilon is some number bigger than 0. So the inequality never changed direction. So what did I just argue? I just argued that if I want this to be true, if I want all my values to be within epsilon of L, I have to go out to N bigger than 1 over epsilon. So what we've done is we've found that big N. So in other words, for all natural numbers bigger than 1 over epsilon, that statement will be true. And so what we've proven is that really is the limit. Because no matter how small an epsilon you pick, I can tell you how far out we need to go. So for example, if you want to be within a half, epsilon of a half, you'd have to go out past 2, right? Because right at a half, it would be right at the boundary. But after that, all points are within a half. 1 over a half is 2, right? If you want to be within 1/billionth of 0, you just need to go out past 1 over a billionth, or out a billion terms. But we've proven that it's true for all epsilon because we didn't specify the epsilon. We just said, take your pick. Any number bigger than 0, if we go out to 1 over that number, everything else out past that will be within epsilon. So we've proven that the limit equals 0. Now, just like we did for functions, this can be hard to do with complicated expressions to prove that this is true. So we're not going to prove things by the definition. We're going to use a series of properties and theorems that are true about sequences that allow us to sort of indirectly show limits as opposed to going to an epsilon proof every single time. So we'll look at some of that stuff coming up.